So welcome back to the course of advanced algorithms. Today we'll talk about a very interesting topic about the categories of the problems. And if to be more specific, we will talk about P, NP, NP-complete, as well as NP-hard. So for today, the plan is very simple. So as you can see, the plan is the same as the title of the lecture. So first we will start with the P. But before starting everything, we need to define or remind ourselves the type of the time complexities. So as you know from the introduction to algorithms, here are the time complexities. This one is a constant. Big O of log n is logarithm time complexity. Big O of n is linear, and this one, big O of n power of c, is polynomial time complexity. Actually, big O of n, which is linear, is like special case of the polynomial time complexity because it is like big O of n power of 1. And the last one, big O of c power of n, is exponential. So c is a constant, n is a variable. It's like size of our input. Actually, in the world, it is well known that if we have some like algorithm that runs in exponential time complexity, is not good, and that's why all the solutions, if we have some algorithm, we always try to solve that. We always try to find solution in a polynomial time complexity, because polynomial time complexity is like counted as a good time complexity. It's a time complexity that like reachable in a good amount of the time. So what is the P? P is some kind of class of problems for which we can find solution in a polynomial time complexity. Again, the polynomial time complexity is big O of n power of k. K is some constant, and n is the size of our input. So if we can solve some problem in a polynomial time complexity, it means that that problem belongs to the P. Next one is the NP. NP is quite different. NP, if NP says the problem that belongs to the NP is the problem that solution for that we can verify, or in other words, check the solution in a polynomial time complexity. If we can verify or check the solution in a polynomial time complexity, it means that it is belong to the NP. But it doesn't mean that the solution to some problem runs in a polynomial time complexity. Also, guys, please pay attention on the certificate. Certificate means the solution to some problem. If we can verify certificate in a polynomial time complexity, it means that it is NP. In other words, we can also say that the NP is some kind of class of decision problems. What is a decision problem? Decision problems is problems where we can answer yes or no. And these decision problems, the solution to these decision problems can be verified, again, please pay attention on that, in a polynomial time complexity. So here is a big question in the world of maths as well as in the algorithms world, is that is P equal to the NP? There is no answer yet to that question. There is no proof that P is equal to the NP, or there is no proof that P is not equal to the NP. And why it's like that? Because as I said before, if we can verify solution or verify a certificate to some problem in a polynomial time complexity, it doesn't mean that the solution is in a in the polynomial time complexity, and as well as there is no proof that if we can verify solution in polynomial time complexity, we cannot solve that problem in the polynomial time complexity. There are some problems where uh, we don't know yet the polynomial time complexity solution to some problem, but it doesn't mean that they don't exist. That's why we cannot prove that P equal to the NP or P is not equal to the NP. And this problem, this question is one of the 7 Millennium Prize problems in the math. If someone is able to prove one of these statements, will get $1 million. So if you're looking for the 1 million, so you have a good chance to try to prove one of these two statements. Next, it's a reduction. So what is a reduction? Actually, reduction is some kind of technique to convert one problem to another problem. In other words, convert instance of, let's say, problem y to the instance of the problem x. This is called reduction. What does mean reduction? What does mean instance? In other words, it is a way to convert the input of the problem y to the input of the problem x. Why do we need that? We need that because if we are able to convert or reduce the problem input of the problem y to the input of the problem x, it means that we can use solution to the problem x also to the problem y. So here is we can use two notations. Any of them is fine to say that this is reduction. Like here, we reduce the problem y to the problem x. Or we can use this notation to say that we are reducing the problem y to the problem x. Also, there are some kind of requirements for reduction. So let's say that we want a function f that maps y to x. F is in polynomial time. It means that the reduction should be done in a polynomial time complexity. In that case, it would be counted as a reducible. If a small y is a element of the iy, so if we can again solve problem x, if we are able to reduce one problem to another one, it means that we can solve that problem. So we need again the reduction to reduce the input of y into the input of x, then solve x, and then we reduce the solution back to the y. And next, it is the main part of our lecture, is NP-complete and NP-hard. So what is NP-hard and what is NP-complete? So let's say it's two categories of the problems. So if how do we define that some category is NP-hard, which category is NP-complete? So we take if a problem X is NP-hard, and it means that every problem that is in Y that belongs to the NP are reducible to the X. And what is the NP-complete problem? In order to define that, if a problem X is NP-complete, it means that X also belongs to the NP as well as X is the NP-hard. So actually the NP-complete is most difficult NP problems. What does mean most difficult? It means that they take a lot of time to solve that problem. The time complexity is very big. So here is the Euler diagram for to show the categories like relationship of this part of the problems. As I said before, we don't know yet is P equal to the NP or P is equal to the NP. By the way, nowadays most of the people they believe that P is not equal to the NP, but there is no proof to that yet. So if P is not equal to the NP, then here is we say that P is like subset of the NP, like but if you take a look on here on the complexity, the P is like less complex problem, like in terms of the time complexity. And as I said before, NP is a type category of the problems where the certificate of the solution can be verified in polynomial time complexity. So NP-complete is a kind of like it also belongs to the NP hard as well as to the NP. And the NP-complete is the most difficult problems here in terms of the complexity, in terms of the asymptotic analysis of the problem. And NP hards are the most difficult problems. And if P is equal to the NP, then we would have this kind of diagram where all the problems that are in P also is a P, and some part is in NP complete. So why do we need reduction? Reduction allows us to show to which category does some problem belong to. For example, if we have some problem B and that problem is P, and if we are able to reduce the problem B to the problem A, then we can also say that it is a NP. If some problem is is B, sorry, this should be P. If we have some problem B, which is the NP, and if we are able to reduce it to the problem A, then it means that problem A also belongs to the NP. If some problem is A, if some problem A is NP hard, and if we are able to reduce it to the problem B, then we can say that problem B is also NP hard. How it's these problems B are well-known problems usually. So we usually, if in order to prove that some problem is belong to some of the categories, we just take some famous problem that belongs to one of the like classes of the problems. Then we reduce that, prove that there is like polynomial time reduction. Then we can show that that problem belongs to some specific class of the problems. So if we can also, after the reduction, also reduction shows us that if we can if we are able to reduce problem A to the problem X, also it means that if we can solve the problem X, we can also as well solve the problem Y, and vice versa. If we cannot solve Y, we cannot solve X. So also if we are able to reduce Y to the X, it means that X is at least as hard as Y. It means that it's not, for example, if we say that problem Y is NP hard and we are able to like reduce it to the problem X, it means that for sure we cannot say that it is a P. It is at least as hard as Y. Also, one more time, if we are able to reduce some well-known problem Y to some problem X, it means that, and if we can solve the problem in a polynomial time, then we can say that Y is also solvable in polynomial time complexity. So if Y is hard, then X is at least as hard as y. So please remember these two statements, because it may be necessary to prove you some problems that belongs to some specific class of the problems. So here is a way to show that some problem X is NP-complete. So if we take a look on the definition of the NP-complete, it says that NP-complete, so let me go back. So NP-complete says that if X is an NP and if X is an NP-hard, then we can say that it is the NP-complete problem. So in order to show some problems that, in order to prove that some problem is NP-complete, first we need to show that that problem is NP, which means that we can verify the certificate of that solution of that problem in polynomial time complexity. And second step, we need to show that this X is NP-hard. And in order to show that this is NP-hard, we need to take some problem that we already know that this problem is NP-hard. Then if we are able to reduce that problem to the X, then we can say that that problem is NP-hard. And if we satisfy these two requirements, then after that only we can say that this problem is NP-complete. Actually, in order to show that some problem is NP-hard, we need to take all the famous problems and we need to reduce all of them, of course separately, to that problem X. After that only we can show that this is NP-hard. But we don't have much time to. There are like very many problems which are in the NP, but we don't have time. That's why we say that if we're able to reduce one of the famous problems of NP-hard to our problem X, if we're able to reduce that, then we can say that this is a NP-hard. So here, why for one of the most famous problem and well-known problem that is proves that it is NP-hard is the SAT problem. I will talk about SAT a bit later. So to show that we have, in order to show that problem X is NP-hard, we take some well-known problem Y. We reduce or transform that problem into the X, and that algorithm should be able to say yes or no. Again, the problem, we need to convert that problem to the decision problem, like where solution is one of the two options. It's a yes or no. So one of the most famous NP-hard problem is the Boolean satisfiability problem, which is also called SAT. So what is that problem? Before defining this problem, we need to define some notations. So we need to remind ourselves what are the Boolean connectivities. So this one means AND, this notation means OR, and this one is not. So what is a formula? Formula is a conjunction normal form if it is conjunction of the clauses. So what is a clause? Clause is just a like disjunction of the literals. What is a literal? Literal is just a variable of or is a variable or its negation. So here is the example. So we have three kind of literals or three kind of variables like x1, negation of the x2, negation of the x1, x3, negation of the x2, and x3. And we have this kind of or connectivities like here. And this everything inside this one is clause, like conjunction, disjunction of the literals. Everything inside of the parentheses should be connected with the OR. This is a first like one clause, this is the second clause, and this is the third clause, and everything is connected with the AND operator. And our problem is to find case where this formula can be satisfied, or this problem will be true. So for this problem, again, this problem is NP hard. It means that the problem to this problem, solution to this problem is bigger than the polynomial time complexity. In order to solve this problem, we just need to guess every possible value for these literals. Here for this formula, if we take this kind of values, like let's say that x1 is a true, x2 is a false, and x3 is a true, in that case only we can say that this formula is true. So this is example. So next one is the 3-SAT. So what is the 3-SAT? It is actually SAT problem, but we use at most 3 literals. So let's say that we have this kind of formula. As you can see, on each of the inside of the each clause, we use at most 3 literals. And for this kind of problem, we need to find the case values of the literals where we can satisfy the formula. The case where we can say that this formula is true. So again, this problem is a hard. Hard means in terms of the complexity, like time complexity, and there is no polynomial time solution for this problem. But we can verify that solution is in polynomial time. Like for example here, let's say that we have this problem, and one of our friends says that actually the solution to this problem is this one. So what do? We just set values to each, like change values of, put the values of these literals inside of these clauses and check can these values give the answer true. So even though the solution is not in a polynomial time complexity, the solution is in, like the verification of the solution is in polynomial time complexity. This big direction of the classes of the problems were firstly defined by Cook and independently by Leonid Levin. So in 1971, Cook showed that the SAT is the NP-complete problem. So he took every possible problem that is well known from the NP-hard, and he was showed all the proofs, all the reductions to the SAT, and showed that SAT is NP-complete. Actually, the proof is very long because it involves a lot of the problems. So that's why it may take not only one lecture, and that's why we just say that SAT is the NP-complete problem as it is. So here is the first example. So let's say that we have independent set. So this is one problem. So independent set is just first we have the graph, as you can see here. This is an undirected graph, and the independent set is just a set of the vertices where there is no edge between them. For example, for this graph, here are the independent sets. It's like 1, 4, 3, 4, 5, 1, 4, 5, 6. So here, as you can see, between 1, 4, there is no edge. So this is the independent set. Here is the 3, 4, 5. There is no. There is between 3, 4. We don't have any edge, common edge. Between 3, 5, there is no common edge. Between 4, 5, there is no common edge. As well as for this set. we can see that this is independent. So right now our goal is to prove that this problem is NP complete. So how can we prove that? Again, reminder, um, in order to show that some problem is NP complete, we need to do the next steps. First, we need to show that problem is NP complete, is a NP, like we need to show that this independent set is NP. Then we need to take some well-known problem y, and we need to able to reduce the problem to the problem x to our problem. So we need to take some well-known problem which is NP hard, and we should be able to reduce that problem into the independent set. If we are able to reduce that problem, it means that after that only we can show that independent set is an NP complete. Again, the problem should be converted into the decision problem, like where the solution to our problem is one of the two options. If it should be either yes or no. So first step, we need to show that that problem is NP. So the first question, is it NP? We need to be able to verify solution in polynomial time complexity. Actually, it's a very easy part. We just take some solution and just check is there edge between some kind of vertices. So for example here, let's say that we have given this solution and we have given this graph, and in order to verify that this solution is correct, we just take every two vertices and check is there edge between them, and after that only we can verify that solution is correct. So the checking the answer would take some polynomial time complexity. This step is very easy. Step 2, we need to show that problem is the NP hard. So we need to pick some problem y, which is we know that this problem is already NP hard, and we need to reduce that problem y into the independent set. We can verify, we can reduce that problem from the 3 SAT. Again here, Cook proved us that SAT problem is NP hard, so we can just take like 3 SAT, which is also NP hard, and reduce this problem into our our independent set problem. So what do? We construct some graph G, and actually we change the definition of the problem, because if you remember here, we need to convert the problem into the decision problem where we have yes or no. So that's why we like change a little bit the definition, and we say that we have some kind of graph. Do we have some independent set of size k? Like, can we get the independent set of the size k? For that problem, we can say yes or no, and we will have independent set of size k if and only if the 3 SAT instance with k clauses is satisfiable. So for each clause, we will use some kind of special gadget that will determine that is that clause true or not, and we need to connect this kind of clauses. And so for example, let's say that we have some kind of graph, and if that graph have k number of clauses, let's say we have 4 clauses, and if we can satisfy all 4 clauses, it means that we have the independent set of size 4. So we have this kind of clauses, and each of the clauses is some kind of special gadget. And if we are able to verify, if we're able to show that it is possible, then we can say that this kind of independent set of size k is possible. So we just convert the instance of the 3 set into the instance of the independent set. So we build this kind of formula. So also we do the next thing, that where the some variable, for example x, and its negation, they shouldn't be in the same clause. They should be in different clauses. So here we draw some kind of graph, and if we connected the we take some variable x, and we connected that variable x to its negations, like here. This for the 4 independent clauses. So we connected x with this x and with this negation x, and we will do the same thing for the literals y and z. Here we did the same thing, and we claim that if this 3 set instance with k clauses is satisfiable if and only if the graph G has independent set of the size k. So here we showed that we are able to reduce 3 set into the independent set. So we for the next, we to show that it is totally possible, we assume that 3 set is satisfiable, and each triangle has a true literal, like each clause has a value. It's totally possible that each clause has a value of true. So if we have this kind of values, let's say that x is 1, this y is 0, z is 0, then we can satisfy this formula. And we can say that each of these gadgets or each of these clauses are independent set. So it's totally possible that we can get from the graph G the independent size of this size k. So one more thing that I would like to say is that if J has of size k, then it also means that we can create the 3 set of the k clauses with the with this kind of values and the literals. So in in the end of the 1970s and beginning of the 1980s, Richard Karp, a well-known computer scientist, he built some kind of diagram where he showed that there is a way to reduce from one problem to another, and like it is better a reduction from one problem to another one. So here is a it all starts with the satisfiability problem, which Cook showed that it is an NP hard. Then this satisfiability problem is reduced to the 3 set, then 0-1 programming, and the problem with the click. So Richard Karp showed that this diagram of the 21 NP complete problems, where it is the best way to reduce from one problem to another. And in 1985, he received a Turing Award for this work. So that's it for today. For today, please read chapter 34 from the book of the intellectual algorithms. And thank you very much. Good luck.